Okay, so in section 8.5, we're going to be introduced to the three-dimensional coordinate system. As the last half of chapter 8, we're going to start dealing with things in 3 dimensions. So when we talk about the three-dimensional coordinate system, we have 3 axes. We have an x, y, and z axis. So our three-dimensional coordinates, our axes look like this. The dashed line, you have to imagine that the half in the lower left-hand quadrant is like sticking out of the board, coming out at you. And this part in the upper right-hand corner is like going back into the board, like into Miss Garcia's classroom. So you have to imagine that kind of in 3 dimensions. So the way we label these axes, this is the part all students hate. So the x is the axis that's coming out of the sheet of paper. The y is the axis that's going horizontally, and the z is the axis that's going vertically on your sheet of paper. This is the positive end of the x-axis, that's the negative end. Positive end of the y, the negative end of the y. The positive end of the z, and the negative end of the z. Oops. Everybody's okay there? So what if we want to plot, say, the point 3, 2, 5? So when we describe an ordered triple like this, we always describe the coordinates in alphabetical order. So x is 3, y is 2, and z is 5. We all okay there? Now, when we graphed points in 2 dimensions, it was very easy, right? Because you're taking something on 2 dimensions and putting it on a 2-dimensional surface like your sheet of paper. To do something, to plot something in 3 dimensions on a 2-dimensional space becomes a little bit tricky because we have to kind of do a projection, but that's okay. So what we're going to do is we're going to start by, I'm just going to put 3 tick marks on my positive end of my x-axis, 2 tick marks on the positive end of my y-axis, and 5 tick marks on the positive end of my z-axis. Everybody okay there? And what I'm going to do right now is kind of build a box. So the base of my box is going to be in the XY plane. So here's one side of the base. Here's the other side of the base. And now I'm just going to kind of draw a parallelogram. So this point here would represent the point like 3, 2, 0. Right? Because we haven't done anything in the z-axis. We've just kind of gone in the xy plane. Is everybody cool with what we've drawn so far here? Okay. What we're going to do now is we're going to lift this point now into 3 dimensions, because right now what essentially we did was graph a 2-dimensional point, right? We plotted the x and y. We haven't done anything with the z. So to do that, I'm going to start with drawing the sides of my box now. So I'm going to draw the vertical side on the z-axis, and then the matching vertical side from the y-axis. Then I'm going to draw a side that's basically the same length here from the x-axis, and start making my, and then I'll draw another side the same length as that other one I just drew to kind of complete my box. And this point here then is my point 325. So basically what we did is we had this plane in the XY, right? And we went ahead and lifted that plane 5 units. So if the point before was 320, since we've lifted it up 5 units in the Z direction, it's now at the point 325. Can we all kind of see that? Now that's not trivial, right? That takes a little bit of practice, but it's not, you know, the hardest thing that we've ever done this year. It just takes a little bit of, you know, some neatness. Some of us will be challenged just by the drawing aspect of it, that have a little bit worse penmanship, or at least aren't able to summon good penmanship when it matters. Some of us have bad penmanship, but can still summon a decent looking picture when it matters. I'm one of those people. You know what I mean? So, oh, gee willikers. So that's plotting a point. What if instead we wanted to graph the component form vector to -3, 4? Well, we're going to plot a component form vector in 3 dimensions, just like we would plot a component form vector in 2 dimensions. Namely, we're going to plot the point to -3, 4, and then draw a line going from the origin to our point, and put an arrow where the point is. So it's not much different than plotting a point, right? So again, I'm going to just label my axes because it's a new labeling order that I'm still trying to get used to. I'm going to go ahead and plot some points, or make some tick marks. So 2 on the positive x, 3 on the negative y, and then 4 in the z direction. Everybody feel okay there? And just like before, I'm going to start by drawing kind of the base of my box. It's usually a little easier if I have a piece of paper with a ruler on it, but we'll make do with Mr. Kulik's scuzzy penmanship on this one note that he's just kind of freehanding. Everybody feel okay with the base of our box? Okay, so now we're going to lift the sides. Again, I usually start by lifting on the y-axis. So we lift at the origin and then at the other spot on the y-axis. Then we'll lift in the other 2, about the same height. So that's the point to -3, 4. But I want the vector, so the component form vector starts at the origin, and then its head is at the point to -3, 4. So my vector then is the piece in red that I've drawn there. Does that make sense to you guys? Because it's a vector this time and not a point, right? That's the component form vector because I used wedges instead of parentheses. Jack?
So, sorry. Yeah, so when you're moving the plane upwards for the z direction, for the line in the front, I don't know how to describe this. Like the line from the original point we drew.
You're talking about this right here.
Yeah. So you made that like slightly shorter than the one going up from actually?
Well, it's actually, I think, the same length. It doesn't go up as high because.
You have to make it look like a box.
Yes.
Okay, sorry.
That's okay. That's okay. But if you measured the two segments, they should be the same length. But because you're starting further down, it doesn't go up as high. You know what I mean?
Yeah.
It's hard to, it's the vocab and describing what's going on there is sometimes challenging for everybody. Is that okay though?
Yeah.
In general? Okay. So again, just takes a little bit of practice. I think part of the problem set is just plotting some points in 3 dimensions to get some practice on that. When you do that, I do expect to see the box. If you want to use colors, you're welcome to do that, or you want to do dashed lines, whatever makes it easier for you, you know, make it easy for you. I'm very flexible on that. So when we plotted points in 2 dimensions, we also were able to then find like the distance between 2 points or the midpoint between 2 points, right? So we should be able to do the same thing in 3 dimensions. So in 2 dimensions, the distance formula was x1 minus x2 squared plus y1 minus y2 squared. But now we have this third component, right? We have z components in 3 dimensions. But that's not a big deal because the distance formula would just add on a z component piece, and it's exactly like it was before, just, oh, okay, that's nice, like as expected, nothing weird there. That's as nice as you would expect, right? Or could expect. So our midpoint in 2 dimensions was x1 plus x2 divided by 2, and then y1 plus y2 divided by 2. But in 3 dimensions, we also have a z component, but that's not a big deal. We'll just do the same thing for the z component. And everything works just as you'd expect. Nice and simple and easy, right? As far as 3 dimensions go. Okay. So in 8.6, we talk about 3-dimensional vectors. And most of what we're doing in 8.6 is just redoing the terms and definitions and forms that we had in the previous sections for 2 dimensions, just now into 3 dimensions. So in 2 dimensions, our component form was just like AB. In 3 dimensions, it's just ABC, right? In 2 dimensions, the IB component form was the column vector AB. In 3 dimensions, it's the column vector ABC. In 2 dimensions, our linear combination form was like AI plus BJ. In 3 dimensions, we also then have plus CK. Remember these vectors I, J, and k have special names. These are the standard unit vectors. Remember, in 2 dimensions, we just need 2 standard unit vectors, I and j, where I is 1, 0, and j is 0, 1. In 3 dimensions, we need 3 unit vectors, or standard unit vectors, which we can see here, right? So remember, in 2 dimensions, we use the head minus tail rule to take 2 points and convert them into a component form vector. We can do the same thing in 3 dimensions, but instead of having 2 components to our component form, we just have 3 components, but it still works the same way. Head minus tail, head minus tail, head minus tail. So far, everything looks pretty nice, right? None of this seems unusual. Everything's kind of working the way we'd expect it to. Let's say, so that's those different vector forms. Talk about vector operations. So magnitude in the first chapter, or in the previously, if we had a vector in component form in 2 dimensions, its magnitude was just like the x component squared plus the y component squared, all square rooted. 3 dimensions, it's just the x component squared plus the y component squared plus the z component squared, all square rooted. Nothing funny there. You know, vector addition is going to work the same way. Or if I add the 2 vectors, we just add their components. We add the x components, we add the y components, and then we add the z components. If I do subtraction, the same thing. I guess maybe let's do this. Put that up there. I'm gonna grab this stuff. Move you down there. Grab this stuff again. Oops. All of it though. Put you over here. There we go. That way I don't have to recopy this every time I want to use. Oops. And again, the vector subtraction works the same way. I guess maybe we should write these in the order. With addition, it doesn't really matter. But scalar multiplication works the same way. Dot product works the same way. All our dot product properties that we talked about for 2 dimensions hold in 3 dimensions. So far, nothing is really different, right? It's just like, okay, there's a third component, but like everything works the same way it did before. Everybody agree with that? Here's where that stops. What haven't we talked about here yet in 3 dimensions that we talk about all the time in 2 dimensions? Direction. How do we, and when we describe a direction in 2 dimensions, what do we often use? An angle measure. What the heck does an angle measure turn into in 3 dimensions? It's like a sphere, which is kind of a nightmare. We'll talk about how we kind of deal with direction in 3 dimensions a little bit later, but we're going to be done with trying to describe it with an angle. We're going to start describing directions with vectors in 3 dimensions because it makes life a lot easier. But we're not going to mention that now. We'll get to that in a future section. So everybody feel okay with what we've done, which is not a lot, right? Let's run through a couple of one numeric example. So let's say I have vector u is the component form vector -2, 4, 7. Vector v is the linear combination form vector 7i minus 6j minus 9k. And I want to do 2u plus v. Well, first thing I would do is I would convert vector v from linear combination form into component form. Just like I would have done in 2 dimensions. The x component is the coefficient on the I, the y component is the coefficient on the j, and the z component is the coefficient on the k. Cool? Okay, scalar multiplication works the same way. So 2 times -2 is -4, 2 times 4 is 8, and then 2 times 7 is 14. And when I add the vectors together, I just get the vector 3, 2, 5. So vector operations in 3 dimensions, basically all still the same thing, right? Not difficult. Unless the 2-dimensional stuff was still difficult for you, which it could be at this point, right? But not really any worse than 2-dimensional things. That's it for these 2 sections. We're going to stop right here. At this point, you guys could be able to do up through 94. Again, think about what the kinds of things we did, though, in these examples. It was all fast and pretty trivial things, right? Just doing vector operations, plotting points, drawing a vector. Not difficult skill-wise, but like you got to keep sorted the notation and keep your formula sorted and like how you do these little vector operations, but it's still the same rules essentially as 2 dimensions. You know what I mean? So don't think about this as new stuff, but think about it as like extensions on stuff we already know, which is good, right? That's what I'd prefer, is to take something I know and just build it out a little bit more, because it's not new then, it's just like adding on to things I already have. So I've already got it like a mental folder built for this. Okay. The remainder of our time we'll spend doing this homework quiz that you guys all knew were coming.